Hello everyone, this video is brought to you by the Atılım University OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 10. A spherical ball is rolling at point 1 without slipping at v1 equals 4 meters per second. It continues to roll around the inside of a vertical circular loop of radius R equals 45 centimeters. A. Find the speeds v2 and v3 of the ball at points 2 and 3 respectively. B. Determine whether the ball will follow the track at point 3. C. Find the magnitude and direction of normal forces at points 2 and 3. Here, since small r is much less than the capital R, you may ignore the small r in the potential energy calculations. First of all, we write the given quantities in SI unit system. M is 200 grams and it is converted into kilograms as 0.2 kilograms. Speed v1 equals 4 meters per second. Capital R is given by 45 centimeters and it is converted into meters as 0.45 meters. And rotational inertia I is 2 over 3 m times r squared. In part A, let h be the final height of the ball. Then conservation of energy gives 1 over 2 m times v1 squared plus 1 over 2 I times omega 1 squared equals 1 over 2 m times v final squared plus 1 over 2 I times omega final squared plus m times g times h. Here we use omega equals v over r and I equals 2 over 3 m times r squared. Then we obtain 1 over 2 m times v1 squared plus 1 over 2 times 2 over 3 m times r squared times v1 squared over r squared equals 1 over 2 m times v final squared plus 1 over 2 times 2 over 3 times m times r squared times v final squared over r squared plus m times g times h. After the necessary cancellations, we obtain 5 over 6 v1 squared equals 5 over 6 vf squared plus g times h. Here, since we are interested in final speed, then v final equals square root of v1 squared minus 6 over 5 g times h. For point 2, h equals capital R and this equation gives v2 equals square root of v1 squared minus 6 over 5 times g times capital R. Putting the corresponding numerical values into this equation, we get 3.2723 meters per second, or approximately 3.27 meters per second. For point 3, h equals 2 times capital R. and equation 1 results in V3 equals square root of V1 squared minus 12 over 5 times G times capital R. Inserting the corresponding numerical values into this equation, we get 2.3272 meters per second, or approximately 2.33 meters per second. For part B, the centripetal acceleration at point 3 is AR3 equals V3 squared over capital R, which is 2.3272 meters per second squared over 0.45 meters, which is greater than the gravitational acceleration G, which is 9.8 meters per second squared. Thus, the ball must be in contact with the track, pushing downward on it. In part C, we will find the normal forces at points 2 and 3. If we draw all the external forces on the ball at point 2, we find the normal force as N2 equals m times V2 squared over R, since N2 is the only force in the centripetal direction. If we put the corresponding numerical values into this equation, we get N, which is approximately 4.76 newtons, and vector N2 is equal to minus 4.76 I hat newtons, since it is in the negative x direction. At point 3, the free body diagram for the object is drawn like this, and the Newton's second law gives N3 plus m times g equals m times V3 squared over R, and we obtain the formula for N3 as m times V3 squared over capital R minus G. Substituting the corresponding numerical values, we obtain approximately 0.447 newtons, and vectorially N3 is approximately minus 0.447 j hat newtons, since it is in the negative y direction. Okay, this brings us to the end of the discussion of this problem. Thank you for your attention, and see you in the next lecture.